Welcome to the TheMediaWard podcast. You tend to assume that when a new building goes up, the architects and the construction teams have ensured that it's safe. You hope they've made sure it won't topple over, collapse, shake, or pose a fire risk, yet that's not always the case. Sometimes that's down to cost-cutting measures, other times it's incompetence, and occasionally it's plain old human error. We're going to take a journey through a few architectural mishaps, examine what went wrong, and how they fixed the problems. We start in Seoul, South Korea, with the story of the 190-metre tall Technomart 21 building. The 39-storey building houses offices, sports facilities, as well as a sprawling shopping centre. At around 10 a.m. on July 5th, 2011, the structure began to shake. This went on for 10 to 15 minutes. Most curiously of all, it was really only the top floors where the movement was felt, and none of the surrounding buildings experienced anything of the sort. The building was evacuated, and officials scoured the structure looking for anything that would account for the sudden shaking. The press began to speculate as to the cause immediately, suggesting that the underpinnings of the building were settling or that the wind had caused unusual vibrations. An earthquake was ruled out, given that it was the only building affected. The general public in any country would be concerned about unknown shaking in a tall building, but for the residents of Seoul, the concern was intensified by the memory of Sampoong. In June of 1995, the Sampoong department store in Seoul collapsed, killing 502 people and injuring 937. During the investigation that followed, numerous issues came to light. The original design had been altered significantly with the addition of an extra floor, increased weight on the top floor and roof, and a reduced number and size of internal supports. To top it all off, substandard materials had been selected. Following a trial, the management responsible for making these decisions were imprisoned for a total of 15 years. This was the memory that loomed large in the minds of the people of Seoul when the shaking building incident occurred in 2011. Following an inspection by the Korea Infrastructure Safety Corporation, a quasi-governmental agency tasked with preventing structural accidents, the building was deemed safe, but the cause of the vibrations was still undetermined. This was obviously alarming for the residents of the building and its neighbours. The shops within the building saw footfall diminish along with their revenue, so there was great pressure to identify the source of the mysterious shaking. While the investigation was ongoing, 2 more incidents occurred. About a month after the vibrations were first felt, a section of the ceiling on the 10th floor collapsed. This was immediately reported to the authorities and fueled further concerns as to the building's structural integrity. After investigating the damaged ceiling structure, footprints were found, along with additional signs of damage. It turns out that a safety inspection of the ceiling had taken place shortly before its collapse, and the damage to it had actually been incurred during that inspection. The partial ceiling collapse was deemed unrelated to the previous shaking incident. Just as the overarching investigation was coming to a close, another short series of vibrations was experienced in the building. This was reported to the investigation team and actually helped to support the conclusion that they had already reached. The investigation into the cause of these vibrations was undertaken by a team from Dankook University, aided by an engineer from a Korean engineering firm. The preliminary research had already ruled out settling of the foundations or an earthquake, so other possibilities had to be looked into. The first possibility was wind load. As the wind blows and exerts pressure on the external surfaces of the building will flex. It is possible that this movement results in vibrations and shaking if the wind is strong enough. The next consideration was the possibility of vibrations emanating from the air conditioning control room. While the mechanics of these systems don't generate significant vibrations, should the vibrations create a resonance-based feedback, they could potentially cause significant building movement. Generally, if an object is sending out vibrations to its surroundings, they dissipate. But in certain circumstances, they can build up and intensify. This is the basic idea behind resonance. There happens to be a 4D theatre on the 9th floor of the building. This theatre uses chairs that rumble, along with powerful speakers to increase audience immersion. This was another cause that was considered. There is also a fitness centre on the 12th floor of the building. There was a suggestion that the vibrations of treadmills being used, or the rhythmic aerobic exercise classes, could build and grow if they hit the resonant frequency of the building. The investigation team reviewed the design of the building and found that it met all structural design standards. They compared the plans with the building itself and found that it matched perfectly. As far as they could tell, there was nothing wrong with either the building's design or its construction. To investigate the first possibility, that of wind load, the team first turned to the Korea Meteorological Administration. Amongst other services, they provide wind speed data for the country. At the time and date of the original shaking of the building, they reported that the winds were in fact less intense than usual. This implied the wind load wasn't the culprit, but the investigation team wanted to confirm that it was not the cause, as wind load is a fairly common cause of building movement. Incidentally, a typhoon was on the way, so the team set up a number of instruments throughout the building to measure any movement as the typhoon passed through the city. The high-speed winds of the typhoon passed by the building, exerting many more times the pressure on it than was experienced during the first series of vibrations, but no excessive movement was detected. Therefore, wind could be ruled out. The next option, vibrations from the air conditioning equipment, was also quickly ruled out. The machinery was inspected and found to be in working order, and as it is in continuous use, intermittent vibrations would not be a likely occurrence. The vibrations produced by the machinery are also of a much higher frequency than the resonant frequency of the building, meaning that they would not be amplified by the building. The 4D theatre, that creates a more immersive experience via mechanical vibrations of the seats, was ruled out as a potential cause, due to timing. The theatre had showings throughout the day, but the theatre was empty at the time of the first vibrations. The final consideration was the fitness studio. It houses a number of exercise machines such as treadmills. There are also spaces for group classes such as Taebo, an aerobic exercise regime that combines movements from boxing and Taekwondo. This explanation stood up to scrutiny. There was indeed a class going on during the first series of vibrations, and it was being led by a new instructor who was working the 23-member class harder than the previous instructor. A simulation of the class was conducted with the same number of people as the original class. They positioned movement sensors throughout the building, focusing on the higher floors, where the strongest movement was felt during the original shaking incident. The effect wasn't immediately apparent, but as the experiment progressed, the vibrations felt, especially on the upper floors, increased in severity. The movement peaked at around 10 times the normal vibration levels of the building. It became clear that the exercise class was the cause of the building shaking. How does an exercise class comprised of 23 people result in a 39-story building shaking violently enough that its occupants are evacuated? It all comes back to that resonance phenomenon. The rhythm of the exercise, the location of the studio, and the specifics of the building design all serve to amplify the movement throughout the building. The lead investigator had this to say on the matter. The case of this building is very unusual in that resonance occurred in the longitudinal direction of the structure due to a group rhythmic exercise of humans, and the amplification of displacement was too small to have an impact on the safety of the building, yet it caused discomfort to the users of the building. When an external vibration hits the resonance frequency of a certain object, the vibration is amplified and causes excess shaking even from slightest movement. It just so happened that the rhythm of the Taebo class coincided with the natural resonance frequency of the building. It wasn't a designed flaw in the building, it was merely an unfortunate coincidence. We continue our story in London, England. A 37-storey building that was being constructed in the financial district of the city had been nicknamed the Walkie-Talkie on account of its distinctive shape. The building's glass and steel form widened towards the top, lending to a unique appearance. One day, Mr. Martin Lindsay returned to his car that he had parked on a street in sight of the building to find a note on its windscreen. It read, "Your car's buckled. Could you give us a call?" accompanied by contact details for the construction company who were building the walkie-talkie. The curved glass face on the unfinished building had reflected and concentrated the sun's rays down onto the street. The heat produced had caused some of the plastic parts of Mr. Lindsay's car to warp and melt. Businesses on the street began to notice paintwork blistering, tiles cracking, and holes being burned into carpets. One calf demonstrated the effect rather pertinently by frying an egg outside their establishment, using nothing but the rays reflected from the building. The walkie-talkie had earned a new nickname, the Walkie-Scorchy. The original design had called for horizontal sun louvers on the south-facing side of the building, but these were cut in a cost-saving design revision. The designer had realised that his building would reflect and concentrate the sun's rays, but had estimated the resulting temperatures would only be around 36 degrees C, not the 72 degrees C that was actually generated. For our American friends, that's 97 Fahrenheit and 162 Fahrenheit. The architect, one Raphael Vinoli, has had a few incidents with his buildings causing hotspots due to their reflective surfaces. The Vdara Hotel in Las Vegas had a similar problem, reflecting the sun, leading to singed newspapers and melted plastic lounge chairs. The solution in that case was to cover the expanse of glass windows with a matte film, reducing the intensity of sun reflected back down to the ground. As a temporary solution to the Walkie-Scorchy's scorching rays, the local council suspended parking on the affected street, and the building company erected a temporary scaffolding shield to intercept the reflected rays. The firm that owned the building released possibly the most annoyingly mealy-mouthed PR statement I have ever come across. A solution is in the final stages of design, and implementation will commence shortly. Despite the solar glare issue of the summer, occupiers have not been blinded to the efficiency and location of the building. After planning permission had been secured, aluminium louvers were attached to the building, which vastly reduced the amount of light that the building reflected. Thus the problem went away, yet the building's nickname, the Walkie-Scorchy, has persisted. We'll be right back after a quick word from our sponsors. Finding good, high-quality, natural dog treats is not always the easiest thing to do. Thankfully, poochiepacks.co.uk has got you covered. Poochie Packs has a dizzying array of all-natural treats for your canine friends, from wild boar strips to salmon sausages. My German Shepherd, Jax, is rather partial to the fish skin cubes. They even offer a monthly subscription service, so your pooch can get the highest quality treats straight to your door. Poochie Packs offers home delivery throughout the UK and free delivery on all orders over £25. For 5% off, and so they know that I sent you their way, enter the code WARD at checkout. That is WARD, W-A-R-D. You can find Poochie Packs at poochiepacks.co.uk. That is P-O-O-C-H-I-E packs.co.uk. Right, back to the show. In the early 1960s, Citicorp, a multinational investment bank, was outgrowing its Manhattan headquarters. Just across the street was a plot of land that looked promising, but there was a catch. St. Peter's Lutheran Church had occupied the site since 1905, but the building was in a state of disrepair. It also happened to occupy the very corner of the lot Citicorp was intent on purchasing. The church was willing to sell the air rights to their plot, that is, allow a building to overhang the church, as long as a few conditions were met. Citicorp would have to build them a new church, in the same location. Citicorp's tower could overhang the lot, but it couldn't place any supporting columns on that section of land, or physically make contact with the church. Skyscrapers in dense cities like New York often have to allow for unusual requirements, so having a building on stilts wasn't unheard of. The location of where those supporting stilts would join the building, however, was new. To accommodate the new church, Citicorp's tower would need to be supported by 114-foot tall stilts, but instead of those stilts being in each corner, they would have to be placed at the midpoint of each side of the building. Each corner of the 59-story building would cantilever out from the central support columns, leaving each corner of the building overhanging by a full 72 feet. This meant that the new church could nestle neatly under one corner of the building. By allowing such a large amount of space to remain at ground level, they were also able to circumvent some zoning laws, allowing the building to rise higher. So high, in fact, that at the time of its construction, it was the 7th tallest building in the world. At the very top of the building is a 160-foot tall angled crown. As one side of the building continues straight up to its tip, On the opposite side, the vertical face turns into a diagonal face, rising to meet the tip of the building. It kind of looks like a glass and steel ski slope. This slope was originally planned to face west to provide amazing views for residential penthouses, but the city refused to grant planning permits for this purpose, so the slope was reorientated to point south. This would allow for increased solar power generation, but due to the limited technology of the time, the solar plan was scrapped. It's now mostly used for housing mechanical equipment, which means the aircon units are the ones with the best views. Anyway, those support columns positioned in the centre of each face would provide less stability than corner-mounted supports, so extra reinforcement had to be utilised. To transfer the loads from the corners of the building into the centrally placed columns, huge V-shaped structural bracings were placed down each side of the building. To complement these structural bracings, a tuned mass dampener was also installed at the top of the building. This 400-ton block of concrete floats on a thin layer of oil and helps to offset the swaying of the building generated by the forces of the wind. As the building flexes in one direction, the mass dampener shifts in the opposite direction, and in doing so can inhibit movement by about 50%. The steel frame, with its all-important V-supporting sections, was initially going to be welded together, but the contractor that was hired to actually erect the building offered an alternative suggestion. By bolting instead of welding it all together, they would save a full $250,000. The bolts would not be quite so strong, but mathematical calculations showed that they would still provide more than enough strength for the purpose. The maths checked out, and it saved a lot of money, so it seemed like a no-brainer. As you might have guessed, this turned out to be the wrong decision. In June of 1978, an engineering student named Diane Hartley was completing her undergraduate thesis focusing on the Citicorp Centre. The building had had its grand opening only a year prior, and its unusual construction would certainly prove to be an interesting topic. As part of her work, she performed her own calculations, evaluating the design's resilience to wind-related stresses. Her calculations were as expected for winds hitting the faces of the building square on, but when she performed the calculations for quartering winds, winds that impact the corner of the building and push against it from two sides, the calculations just didn't work out. In normal buildings, with more substantial footing, the highest stresses are from winds hitting just one side of the building. Quartering winds usually generate significantly less force. According to Diane Hartley's calculations, this was not the case for the Citicorp Centre. The quartering winds posed a more substantial threat, and it appeared that the building would not be able to withstand them. She reached out to the engineering firm and was able to speak with a junior engineer, who insisted that the building was more efficient than her calculations suggested. She accepted this answer in good faith and carried on with her dissertation. Unbeknownst to the student, this question of the quartering winds was passed on up the chain to the lead structural engineer, who decided to look a little deeper into the potential issue. As LeMessurier reran the numbers, he discovered some very peculiar findings. On each side of the building, there were 8 V-shaped supporting braces. When subjected to quartering wind loads, these stresses were not evenly distributed between each chevron brace. Half of the braces experienced next to no structural stress, while the other half experienced double what was expected. In addition to this, when considering structural forces, you can often subtract the dead load of the building from any pushing force. A building has a lot of mass, and that mass is pulling it down towards the ground. This mass will resist any pushing force generated by the wind. You can work this dead weight into your calculations. However, too much of this dead weight was subtracted due to a misunderstanding in terminology when considering the support structures. The supporting V-shaped sections had been considered truss members instead of columns. The difference in how they were labelled led to a halving of the number of connecting bolts. The preliminary calculations LeMessurier had made suggested that the forces the building could withstand were significantly less than previously thought. LeMessurier flew to Ontario to meet with Alan Davenport, a wind tunnel expert. Davenport had modelled the building during the initial design phase and was able to retrieve his earlier modelling. Upon examining the quartering winds, he confirmed LeMessurier's suspicions. the forces the building would be subjected to would be much higher than previously thought. Taking these calculations further, he determined the full extent of the problem. It became apparent that 70-mile-an-hour quartering winds could topple the building. A storm severe enough to generate those winds hits New York once every 16 years or so. That meant that the building had a 1 in 16 chance of toppling over every year. The tuned mass dampener, however, was of substantial assistance. With a dampener in operation, the building could withstand significantly stronger winds, so that the risk of toppling dropped to about 1 in 55. This was still a dangerous margin, but it was better than 1 in 16. However, the dampener had a significant drawback. It needed power to function. The kind of storm that would threaten the building would also threaten the city's power supply. Therefore, the dampener couldn't be relied upon. Lemessurier had a difficult decision to make. Disclosing the building's instability could lead to lawsuits, bankruptcy, and the end of his career. Lemessurier passed away in 2007, but in 1995, while speaking at MIT, his alma mater, he detailed what was going through his head.
No, I agree firm with him. I said, look, if you got a license from the state and a certification for university first, and now you're going to use that license to hold yourself out as a professional, you have a responsibility beyond yourself. If you see something that is a social risk, good heavens, this thing would kill thousands. You must do something. You must do something.
As Lemessurier alluded to, the consequences of the building toppling would be horrific. If the building toppled in the wind, it would crash into its neighbours, likely causing them to collapse. The resulting domino effect could cause a whole slew of buildings from Midtown to Central Park to come crashing down. The loss of life would be astronomical. After resolving to bring the building's issues to Citigroup's attention, Lemessurier decided that he also wanted to present a solution to the problem. The V-shaped bracing structures would need to have their connections reinforced. Luckily, they were relatively accessible. The sections that needed reinforcing, through the application of welded metal sections, were between the floors of the building and were accessible from the inside. On advice from an attorney, he contacted his professional indemnity insurer, who made some suggestions as to how to go about disclosing the error. After some carefully coordinated requests and meetings, Lemessurier found himself in a meeting with the chief architect of the building alongside the chairman and executive vice president of Citigroup. Lemessurier laid out the findings and presented his proposed solution. As opposed to the Citigroup representatives becoming adversarial, as might have been expected, they were primarily concerned with how best to begin rectifying the issues. The first thing that was accomplished was installing emergency generators in the building to keep the mass dampener active in the event of a power outage. With that, they had to begin the process of rectifying the building's fatal flaw. The plan was to weld more than 200 2-inch thick, 6-foot-long steel sections alongside the pre-existing bolted connectors, providing a more robust connection. In the meantime, other steps were taken to safeguard the building. The manufacturer of the tuned mass dampener provided round-the-clock technical support to ensure that any faults arising with the unit would be fixed as quickly as possible. Strain gauges were placed on structural members to monitor the stresses that were passing through them, and a group of weather experts were retained to provide weather reports multiple times per day. Once the detailed plans for renovating the building had been produced, they were submitted to the local government in order to obtain work permits. Up until this point, only a small number of people were aware of the building's instability, but with the plans now going to the planning department and therefore becoming publicly available, the world would soon learn about the potentially disastrous design flaw. Citicorp sent representatives to the American Red Cross and the NYPD to formulate an evacuation plan should a storm approach that was liable to topple the building before repairs could be completed. The evacuation plan encompassed a 10-block area of Manhattan, and the Red Cross estimated the potential death toll, if the building collapsed without any evacuation, at up to 200,000 people. Citicorp issued a rather bland statement, attempting to downplay the severity of the situation, labelling it as a preventative measure, rather than a fix for a serious problem. As the plan circulated and awareness of the severity of the situation grew, the press inevitably caught wind of it. As Citicorp continued to downplay the situation, reporters began to circle. Lemessurier returned to his office to find that a reporter from the New York Times had been trying to reach him all day. Reluctantly, he returned the call, only to be greeted with an answer phone message informing him that a strike had just closed down all of the newspapers in the city. This 88-day-long strike was down to a disagreement between 3 publishers and the Pressmen's Union. With newspapers out of action, there wasn't really any news, unless repairs to the building could proceed without too much fanfare. As repairs were underway, the meteorological team delivered some bad news. Hurricane Ella was advancing up the east coast, bringing with it winds topping at 125 miles per hour, well in excess of what would be required to topple the tower. An army of welders raced to complete the repairs, and the local authorities were hours away from initiating the evacuation process, when, with a stroke of luck, the hurricane turned away from land and headed out to sea. The disaster had been averted. Only 4 months passed between the design firm receiving the engineering student's phone call and the building being fully renovated. The work was able to be carried out overnight whilst the building was empty, so its occupants were none the wiser. Not only had a major disaster been prevented, they'd even managed to carry out the necessary repairs without too much public scrutiny. The building was now able to withstand the kind of storm that would on average hit only once every 700 years, making it one of the safer buildings in the city. Lemessurier's initial cost estimate for the repairs was around $1 million, but in the end the work amounted to in excess of $8 million. The actual figure has never been disclosed, but Citigroup settled for a $2 million contribution. In 1995, The New Yorker broke the story, detailing the severity of the problem and what could have happened if the building had toppled. Having remained under wraps for almost 17 years, the truth was finally out. As it turns out, the story has generally been cited as an example of ethical engineering, with commentators praising Lemessurier's actions in fixing the problem as opposed to burying his head in the sand. Even the most accomplished architect or structural engineer gets it wrong sometimes. As technology advances, our ability to model structural loads improves, but these models are yet to be perfected. Despite everyone's best efforts, calculations and estimates don't always pan out in the real world, and I expect the future holds yet more architectural mistakes of the sort we've heard about today. If you like the podcast, you might like my YouTube channel. Find it at youtube.com/TheMediaWard. If you want to support the podcast, please rate it, subscribe, or share it with a friend. It all helps more than you might imagine. If you want to be even more amazing, perhaps you might consider supporting me on Patreon. There you'll find ad-free episodes, get access to episodes 2 weeks early, meaning the next episode is already available for patrons, and on top of that, 1 extra episode every season. You'll also get access to behind-the-scenes content for the YouTube channel, such as extended cuts and bloopers. You can find me at patreon.com/TheMediaWard. I'd like to thank St. Valentine Music for providing all of the music you've heard in today's episode. For a full list of my sources, please visit the website at TheMediaWard.co.uk. And one last thing. For the first time in over 100 years, a new bridge was being built over the River Thames in London. The London Millennium Footbridge is a 325-metre long structure with a striking appearance. With a normal suspension bridge, towers rise far above the bridge and cables descend from those towers to support the main span. The Millennium Bridge uses lateral suspension, employing some rather smart engineering to do away with those tall supporting columns. This allows for an impressive view down the main length of the bridge, showcasing the famous St Paul's Cathedral. The bridge was officially opened on the 10th of June 2000 by the Queen herself, no less, but it was closed just 2 days later. It wouldn't reopen for another 2 years, whilst engineers set about fixing a major issue with the bridge. The bridge was perfectly safe, but it had an alarming tendency to sway when it was in use, leading to its nickname, the Wobbly Bridge. After the fitment of some tuned mass dampeners, like the Citicorp Tower, the swaying was brought under control. 2 years later than planned, the bridge was ready, but its nickname stuck, even now, nearly 20 years later. It's still known as the Wobbly Bridge.